So in the previous video, we got up to the point where we were able to solve for the generating function. And now we're going to use the method of iteration to be able to figure out what C sub n really is to plug into our power series. So remember what we did last time was we made a table. This one's going to be a little bit different than the previous. It's going to take a little bit more work. So C sub k plus 4 is equal to the opposite of C sub k over k plus 4. Alright, so how does this work? So remember that we found C1, C2, and C3 were all equal to 0. Alright, so we have to call that, and C0 is just an initial term. We don't know what C0 is, so C0 is just C0. Alright, it's just like the origin. So let's just plug in. So we plug in 0, we get C0 plus 4, which is 4, is equal to the opposite of C sub naught, or C0, divided by 4. All right, and we don't know what that means because we don't know what C0 is. All right, in fact, we just know that it's the initial term. C5, that's going to be the opposite of C1, because again, now what we're doing is we're plugging 1 in for K, divided by 5. But remember we said that C1 was equal to 0. Remember we did that, we found that earlier when we were solving, we broke off all those terms. So right here, since C1 is equal to 0, that means that C5 is going to be 0. When K is 2, C6 equals the opposite of C2 over 6. Similar to previous, we know that C2 is equal to 0. Okay, remember we found that up here. So that means that this is going to be equal to 0. And then, not surprisingly, C7, which is the opposite of C3 over 7. Remember we said that C3 was equal to 0. So this is 0 as well. Now, that does not mean that C8 is going to be 0, because when we substitute that, C8 is going to be the opposite of C sub 4 over 8. All right? And what we can do is we can say, oh, okay, well, we know that C4 is really negative C0 over 4. So we're just going to substitute that. So we get the opposite of negative C0 over 4 over 8. Or another way to write this, a little bit easier for us, we're not going to write it as 32. I know 4 times 8 is 32. But we're going to write this as C0 over 4 times 8. When you're doing these types of problems, you probably want to go through and leave these as discreetly as possible. All right, so don't simplify them too much. All right, and that's one of the trickiest parts about this series business, is how far is far enough to simplify. All right, now let's keep going because we've only got a few terms thus far. It's probably good for us to get a few more of these. 5. All right, and something very similar to what just happened is going to happen again. When we plug in 5, we're going to get C9 is equal to the opposite of C5 divided by 9. But remember we said C5 was 0. And the same thing is going to happen for C10 and C11, because those are going to be respectively the opposite of C6 over 10 and the opposite of C7 over 11. And if we just go right back up here, C6 is 0, C7 is 0, so these are zeros as well. All right? But C12 is not going to be 0. So it's the opposite of C sub 8 over 12. And remember, C8 was equal to C0, that's a 0 by the way, over 4 times 8. So this is really going to be the opposite of C0 over 4 times 8 times 12. All right. And eventually we'll manipulate this. Okay, but for right now, we're just going to leave it like that. Now, we could very easily show that when K is 9, 10, and 11, we're going to see that C13, is equal to C14 is equal to C15, which is 0. All right. If you don't believe me, just go back and do it for yourself. All right. But just to expedite this process, I'm just going to leave it like that. Now, when K is 12, C16 is going to be equal to the opposite of C12 over 16. And we already know that C12 is the opposite of C0 over 4 times 8 times 12. So we're going to get C0 positive, because we have negative and negative, of 4 times 8 times 12 times 16. All right, so at this point, it looks like each time we're doing this, we're just adding another factor of, so the next one would be C0 over all of this times 20, and then 24. It looks like all the multiples of 4. All right, here's what we're going to do with this, okay, and this is really sneaky. What we're going to do is we're going to write this as C0 over, now we know 4 is 4. We know that 8 is 4 times 2. We know that 12 is 4 times 3. We know that 16 is 4 times 4. And what I'm going to do is I'm going to multiply those powers of 4. So another way to write this, and again, this is really sneaky, is 4 to the 4th. So that's 1, 2, 3, 4 fours. And then we're going to have 1 times 2 times 3 times 4 left. All right? And now you can see that that's going to be a factorial. By the way, if we go back up here to this to C12, all right, we could do the same thing. We could write that as the opposite of C0 over 4 to the 3rd. All right, since this would be 4 times 2, 4 times 3, so it would be a 4, and a 4 to get 4 to the 3rd, 1 times 2 times 3. All right, how did I know to do that? Well, I've just been doing it a long time. And it's one of those things where you're just going to have to kind of find these patterns that are going on. That's what makes series so tough. Hopefully you can start to see some of the tricks as to what's going on. So if we were to make a guess, because that's the whole point of this, let's make a guess for Cn. Now there's two things going on that we have to be careful of, because we can't forget that there's an alternating factor here. All right? So if we make a guess for Cn, Cn is going to be equal to C0 over 4 to the nth power. All right, and when we say n, that's just how many terms that actually contribute to the sum. All right, notice that this doesn't contribute, so it doesn't matter. These don't contribute, so they don't matter. All right, and up here, this doesn't matter. This doesn't matter. This doesn't matter. So there are 1, 2, 3, 4, right? So it'll be the 4th term. And so since there's 4 terms, it's 4 to the 4th. And this would be 4 factorial. So we could write this as C sub naught 4 to the n over n factorial. There's one other thing that we have to remember. Remember these alternating signs? We had negative and then positive and then positive and negative. It seems like they alternate. And you might remember from Calculus 2 that if you have alternating terms, you just throw in this minus 1 to the n. So that's the alternating factor. All right, so what do we get? All right, so y, which is series n equals 0 to infinity, c sub n x to the n, we just substitute that for c sub n. And this is going to be equal to series n equals 0 to infinity. We have c naught. We have minus 1 to the nth power. We have this 4 to the n. We have n factorial. All right. And then we have this x to the nth power as well. All right. Now, One thing that we have to remember though, if we go back up here, it's going to be every fourth power of x that's going to contribute. All right, so you might remember from Calculus 2, again, this is a really sneaky problem, is that when we go back to Calc 2, we have to remember, oh, okay, well, these are the coefficients. So this is the 8th degree polynomial. This is the 4th degree polynomial. And those are the only ones that are contributing, right? So it's not just going to be x to the n, it's going to be x to the 4n. So it's not going to be x to the n, but it's going to be x to the 4n. All right? And again, that's because only every fourth term contributes. All right. Now, another way to write this would be series n equals 0 to infinity. Opposite of x over 4, or x to the 4th over 4, to the nth power. All right, so notice we have x to the 4th, we have minus 1 to the n, we have 4n. They're all raised to the nth power. All right, and then we also have our c naught over n factorial. All right, or if we really wanted to write it a different way, which might be helpful, I'm going to rewrite this just one more time to make it a little bit easier on ourselves. I'm going to factor the c0 out, and we're going to have x minus x to the 4 over 4 to the n divided by n factorial. And you might remember that this looks like that e function once again. All right, so now it's not e to the x, but it's going to be c sub naught e to the minus x to the 4 over 4, right? And that's going to be equal to y. All right. Now, this rarely happens, by the way. Very rarely are you going to get an exact answer like this. All right. Remember, way back, probably about 20 minutes ago, we solved the solution analytically. And here's our solution. Plus minus k e to the minus 1/4 x to the 4th. All right, so let's grab that. I'll try to grab that. And we're going to bring it all the way back down. See if we can insert it as an object down here. All right, and what you'll notice is that these two solutions are indeed the same. All right, so that's pretty cool that we can use a series solution to be able to solve the differential, and then we can go back to Calc 2 and use some of that knowledge that we know about series and their transcendental representations to be able to get to an exact form. Again, very rarely does this happen. Most of the time, we're just going to have to leave it as a series like this. All right, but for the very first types of problems, I'm just using these as examples just to illustrate that they are the correct solutions, just so that way you can believe it. All right, so we have one more example to look through. It's a second order differential, so it's going to be a little bit different than before, because now what we're going to have to do is we're going to have to take a second derivative of our power series.